Hi, we are Team 6 and we are doing an analysis and redesign of a hitch-mounted bike rack. Product overview. A hitch-mounted bike rack allows users to transport their bikes using their existing car tow hitch. The one we'll be analyzing is shown in the photos and allows the bike rack to fold down so users can access their trunk space. This slide illustrates the exploded view of the hitch rack and all the necessary components needed to assemble the product. The parts listed and annotated show all the custom parts needed to manufacture the bike hitch rack, with the exception of 2 pins that are commercial off-the-shelf components.
Through our functional analysis, the primary function for the bike rack is to transport a bicycle. The subfunctions are to secure the bicycle, attach to the hitch, assure dependability, assure convenience, enhance the product, and please senses. From these, numerous basic functions were identified and are explained further in a future slide.
We identified 2 different assembly sequences for the bike rack. Sequence A begins with the bike holder assembly, then attaches the tubes and hitch base later. Sequence B starts with the hitch base, then attaches the tubes and bike holder assembly after. We then analyzed the assembly sequences based on these criteria. Sequence A proved better for ease of transferring and handling, and ease of fastening and joining because the smaller components are attached before the larger, bulkier parts. All other criteria were the same for both sequences. Overall, Sequence A was better when judging based on these criteria.
The function component mapping matrix is displayed here. The matrix reveals 4 functions that must be fulfilled by all components: withstand precipitation, withstand 100 miles per hour, blend color, and enable hand lift. The matrix also reveals that the hitch base, the center support, the elbow support, and the bike holder tube must be designed and manufactured to meet a high number of basic functions.
On this slide, the bill of materials is shown, with each part listed with the associated quantity, material, and manufacturing and assembly processes. Preliminary costs were estimated by using bulk order fastener catalogs, lecture learnings, and prior industry experience to evaluate material and processes, summing to a total of $51.26 per bike rack. The BOM shows that the larger complex parts and assemblies, the unique fasteners and pins, and the functional need for corrosion resistance largely contribute to the overall cost. By evaluating the function component mapping matrix on the BOM, our team identified possible redesigns that could result in a reduction of product costs while still maintaining all critical product functions. We could commonize the W plates and clevis pins, consolidate the tube sections into a single part, and redesign the bike mounts into simple Velcro straps. By referring to the DfM quad chart, we recognize that each of the aforementioned components has a high functional importance associated with it, but have a potential for redesign with their respective high manufacturing costs.
The primary customers for this product are recreational bikers and families who need to transport 3 to 4 bikes at a time, while the secondary customers are frequent bikers who only need to transport 1 to 2 bikes.
The majority of the product functions are the same for both customer groups. The only one that we see as different is rack capacity. The primary customers need to be able to transport 3 to 4 bikes, while the secondary customers only need to be able to transport 1 to 2.
This slide illustrates the differences between our product variants based on our primary and secondary customers, as well as our product classification that Hannah just described. Very clearly, you can observe that one is capable of transporting up to 2 bikes, while the other is capable of transporting up to 4 bikes. Now that the team has the product variants established, we intend to focus on how the assembly sequence is affected by having 2 variants. To do so, we have identified platforms and modules, as you can see on this slide, which will help us identify opportunities to further delay differentiation. On this slide, blue and orange represent the different bike rack variants. To achieve further delayed differentiation, the bike support plate type was made common among both variants. This delays product differentiation and therefore only requires a single common interface between the platform and module parts, as shown in the product family assembly diagrams in the figures on this slide.
After all the redesigns from the interim report were completed, the plastic inserts were identified as a platform part with a high assembly time at 73 seconds. To improve assembly time, the design of the plastic inserts was modified in 3 ways. To minimize part counts, the upper plastic inserts were replaced with Velcro straps. To facilitate orientation, a lip was added to the plastic insert to prevent free rotation in the W plate. To avoid adjustments, a cutout was added to the lip for the metal loop for the Velcro strap on the W plate. The W plates were identified as a module part with high assembly time at 39.52 seconds. This design was also modified in 3 ways. The addition of the Velcro straps reduces part count. Fasteners were eliminated by adding cutouts to the W plates for the Velcro straps. Finally, these cutouts were added to both sides of the W plate to allow for 2 acceptable orientations. The design guidelines used for these redesigns are listed on the slide. The analysis for the design after initial redesigns can be seen on the left side of the screen and yielded an assembly efficiency of 0.2052 and a total assembly time of 233.94 seconds. After redesigns for manual assembly, the design changes reduced assembly time by 13.79 seconds to 220.15 seconds and improved assembly efficiency to 0.23.
Here our team identified 3 key features from the manual redesign that could be modified to improve the automated assembly cost. First, the Velcro straps, which can stick together through the hooks and loops, were replaced by elastic straps that do not tangle or nest easily. Secondly, the separate plastic inserts per plate were merged into single parts in order to reduce part count. Finally, small holes with ramp chamfers were added to the W plates, and respective features were extended off the plastic in order to help align the inserts during installation and constrain them on all 3 axes.
The initial automated assembly analysis revealed a before design total assembly cost of 33.12 cents. The changes discussed on the previous slide decreased that cost to 17.64 cents, which is approximately a 47% savings.
Before we identified material and manufacturing processes, we identified the critical dimensions of the plastic insert. These are circled in red and are the radius of the arc and the distance between the alignment features. It's necessary for these dimensions to be high tolerance because they mesh with the W plate shown on the next slide. Similar to the plastic insert, the critical dimensions are circled in red on the drawings and correspond to the radius of the arc, and also the distance between the alignment features, which are the cutouts on the circular portion of the W plate. These are necessary again so the plastic insert can mesh and fit properly into the alignment features and nest into the W plate.
We selected nylon for the plastic insert and low carbon steel for the W plate since both are low-cost materials with appropriate properties for the product. Based on the selection criteria, we determined that injection molding is the best manufacturing process for the plastic insert, and sheet forming is the most appropriate for the W plate.
Using the cost estimation guide for injection molding, we came up with a total cost per part of 93 cents. The biggest cost drivers were the cycle time and the cost of the material due to the volume and size of the part we were designing.
The design of the plastic insert was modified in 4 different ways to reduce the cost of injection molding. 1. Ribs were added to reduce material volume. 2. Thickness was also reduced. 3. A draft angle was added to facilitate part removal from the mold. And 4. Sharp corners and edges were eliminated. Together, these design changes reduced the calculated price per part of injection molding by 35.15 cents to 57.49 cents.
On this slide, you can see the design of the W plate prior to design for manufacturing cost analysis and redesign. The assumptions of the cost analysis are listed on the left part of the slide, while the component cost is on the bottom. The volume of the bike rack is relatively high at 230,000, so as you would expect, the main component of the cost is the material cost. Here you will see the redesigned W plate labeled with each element of redesign. A cost savings of about 4 cents was achieved while also improving the part for design for manufacturing. The main opportunities for cost reduction were as a result of material reduction by optimizing the geometry for manufacturing. A key consideration here was the slot design was actually optimized to continue to use the 200 kilonewton press so that the hourly machine rate did not go up.
One appropriate product service system would be a rental service, where customers can lease a bike rack instead of purchasing. This eliminates maintenance expenses for the customer, is more cost-effective for infrequent users, and reduces environmental impact through shared use.
The overall benefits gained after all the redesigns are shown here. The time cut down after design for assembly was 13.79 seconds for manual assembly and 15.58 seconds for automated assembly. After design for manufacturing, the money saved per plastic insert was 35 cents and 4 cents was saved per W plate. Some pros of our design changes include lowered assembly time and part costs, the bike holder assembly being more user-friendly and reduced part count. Some cons include the bike holder assembly being less robust. If we continued making design changes, one thing we would look at would be reducing the part count in the area where the rack attaches to the hitch plate. If we started the redesign over, we would research tube and tube bending manufacturing to try and optimize the design for this as well.